What is CAPTCHA and why does it matter? CAPTCHA is basically a way to tell if a user is a human or a bot. It's used to protect websites from things like fake account creation, data scraping, and login attacks. Bots are a big problem because they can automate these actions at a large scale, which can damage systems and businesses and cause harm to potential customers and clients. Why bots are a problem? Bots are a problem because of credentials, stuffing text, fake account creation, data scraping, secret resell bots, and they can damage businesses and systems. Evolution of CAPTCHA. Originally, CAPTCHAs were just disordered text that humans could read, but bots couldn't. Over time, bots got better, so systems moved to image challenges, but now even those can be solved using AI. So because of that, modern systems focus more on tracking behavior instead of just giving challenges. So reCAPTCHA version 2 and version 3. Google's reCAPTCHA is one of the most common systems. Version 2 is the one with the checkboxes, and sometimes they have the image challenges. It also tracks how you use your mouse to interact with the page. And then version 3 is fully invisible and gives a score based on how likely you are human. Problem is that advanced bots can now copy human behavior, which makes these systems less reliable. So Turnstile and HCAPTCHA. Cloudflare's Turnstile is designed to be more private. It doesn't show a CAPTCHA challenge at all. It checks things like your browser and device instead. And then HCAPTCHA is another system that still uses challenges but focuses more on privacy and risk scoring. It's often seen as a balance between security and then user experience. Advanced systems. More advanced systems go beyond CAPTCHA. Companies like Datadome, which are extremely popular, use machine learning and real-time threat data to detect bots. There are also proof of works systems where the user's device has to solve a small competition. This doesn't stop bots completely, but it makes attacks more expensive and harder to scale. In conclusion, no CAPTCHA system is perfect. Bots are consistently improving, especially nowadays with AI, and the most effective approach is using multiple layers of security like behavior tracking, device checks, and server-side validation. And going forward, systems will need to keep adapting to stay ahead of attackers.
All right, so we're going to take a look under the hood, look at some very simple Python program snippets. Those are available at the end of the slide if you want to run those yourself. It's very simple. Just wanted to kind of show in actual code how AI can be utilized to automate a script program. HTML for the CAPTCHA site, Selenium WebDriver, Python from command line. Okay, this is just Fitt's law. It calculates the time required for a person to rapidly move a cursor to a target area. That's kind of what you do in a CAPTCHA. Applications and automation. Offensive AI uses this formula to calculate realistic mouse trajectories. It allows automated agents to simulate basically natural human movement, or at least it attempts to. Successfully prevents linear movement flags by bots. We'll kind of cover a little bit more of that in the code in subsequent slides. This just kind of defines what a Bezier curve is and how it's used in automated evasion. Modern security systems don't look at just clicks, they track a coordinate path of the cursor. Detection algorithms flag things like perfectly straight lines and constant velocities. That's obviously going to be bot traffic. Attackers use this Bezier curve to calculate more natural human movement that mimics something that a human would do in terms of how they move their mouse. So all we're really doing is smoothing out and making a curve over these points that we're going to generate. This is just the math behind a Bezier curve. We have the anchor, the starting point, the target, that's at the very end. It's going to be the last point. Then control points in between. So all we're really doing is trying to smooth those out. This is just the math behind Fitt's law. We're working with distance, width, average time it takes to complete the movement. All right, on the web end, we have action listeners in HTML. These refresh continuously on the frames. These monitor things like keyboard, mouse movement, clicks as well. This is just some simple variance detection. In an actual system, this is going to be far more complicated. But we have right here variance sizes less than 10. Inside of 10 is going to be a bot. All right, so this is a Python implementation of a Bezier curve. Random.randint method generates random points that we're going to use in an attempt to make a unique mouse arc to the capture box image. AI can also do this. The reinforcement is going to come from fine-tuning values with each fail or success. All right, the top method here, get element by ID. That's going to take a look at our mouse cursor over time and check for what's called jumps. If there's like a huge jump in the cursor, obviously that's not something humans can do, so it'll say bot detected. Then down here in our variances, that's where it's going to determine and output a message whether it's human validated or a bot detected if it's more linear. All right, so this starts our mouse and a simple trajectory starting at 0, 0, upper left of the screen. In reality, it's going to start wherever a person has, or the bot has their mouse on the screen. And we're just moving it to 250, 250. That's going to be wherever the first captcha box is. So this incorporates some jitter using a random ints. AI and ML can be used to automate these iterations. What that's going to do is it's going to look back at all the iterations before. Each value is going to be assigned a statistical probability. That's going to determine what the AI uses as the next values in the iteration. The idea is it gets better and better with each iteration as its guesses become more and more accurate. It looks at all the prior guesses as well. You can get into advanced micro jitter. So this kind of simulates a pixel being off on the path, adding a little bit more variation. Simulating a human hand tremor holding a mouse. All right, going back to Fitz's law, one of the variables is speed. So we want to vary our speed as the mouse moves as well. AI can also do this kind of in the same way. Machine learning, it looks at all the past variables and assigns probability to each. You can do that instead of hard coding these delays. All right, so nonlinear acceleration, the implications of Fitz's law from before. This graph over here on the right shows velocity over distance from the start. A human or a bot trying to be a human would accelerate, and then there might be some bounces as you adjust the mouse to the target. You might overshoot the target and then bring the mouse back into the target. That's the bottom one there. All right, so behavioral engines look for this kind of stuff. The moral of the story is if you want to evade, you have to inject variance. A cloud perimeter relies on lots of complicated, behavioral storing. It's running statistical analysis on these incoming telemetry arrays with our mouse. If the array shows that the distance between coordinates is identical, velocity, xy values never deviate from the shortest possible path, the engine is going to calculate a probability of human score near 0.1 that's going to block the request. Not a very high probability that that's a human. So when you inject random ints into the spatial and timing aspects, the Python script artificially inflates its standard deviation. The ML model on the defensive side is going to categorize this telemetry as imperfect, messy, and hopefully validated as human. So even though captchas are susceptible to evasion by incorporating scripts and machine learning, it can still be used as a stop sign, essentially forcing an IP into a validation. If it validates, whether by evasion or human user, a SIEM dashboard can monitor that IP. If it starts making odd traffic, that IP can be dealt with accordingly.
All right, so my part of the presentation is the technical demonstration. What I'm going to do is walk you through is a target website that I created and how the solver script works to beat the captchas, and then what you would actually do to stop this kind of attack in real life. So this is a back end. It's a Flask web application running locally on my MacBook called Secure Login. It's designed to look like a real login page that a company might actually have. It has 4 endpoints. The main page just serves as the login interface. You're going to see in a couple of minutes. And then the slash captcha endpoints is where the captcha images gets generated fresh on every single request. The correct answer gets solved in the server session on the back end. It's never written in the HTML, so there's no way to just read it out of the page source. We have some slash verify on the bottom left is where the solver posts its guess. The server checks it and returns whether it's right or wrong. And the last slash, the get slash event, this is the piece I'm most proud of. The solver script and the browsers are two complete separate programs without the endpoint. Sorry, the browser will just sit there with the counter at 0, while the solver runs in the terminal, and nobody watching could tell you what was happening. The slash events runs what is called a server sent event stream. When the solver posts a guess, the server broadcasts results to the browser in real time, and that's what makes both the window update together without any page refresh. You'll see all this demo working in a little bit. Now, how does the solver work? It uses a Python library called Triple D Docker, which is a pre-trained machine learning module that was successfully built to read CAPTCHA fonts. I don't have to train it on anything; it comes ready to go. Every attempt goes through 4 steps. First, it sends a signal to the server, so the browser shows the amber dot. You'll see it working. It says bot is solving, and then it fetches the capture image. Then the triple D Docker reads it and returns a predicting string. Then it posts that. Then it posts it that guess to slash verify, and the server broadcasts the results to the browser. So now we are in all the things. These captures are not 100% rate. It's about 85 to 97% accuracy on captchas. I set it so it completes 10 attempts, and each attempt is roughly about 1 second. So it total is 10 seconds. So if you have 100, it'll take 100 seconds. The interface time per image is about 12 milliseconds. That's really, really fast. Um, a human doing this manually would take 30 to 60 seconds just to finish the first one. The captcha isn't even being beaten, it's just being completely irrelevant. It just goes through it quickly. And then I think the most important part of this whole group project is actually how to stop this kind of attack. If I could build a device that could go past captchas, imagine a whole hacker group and people can what they can do with more time on than me. So the obvious question is, what do you actually do about this? The first layer is behavior scoring. Something like a reCAPTCHA v3 doesn't show the user any puzzles. It just watches how you interact with the page. Mouse movement, scroll behavior, keystrokes, timing, and assists a risk score. Our solver hits the API directly and has none of these signals. It would score near 0 and get blocked before it even touches the form. The second layer is a server-side token validation. Lots of sites only check the captchas on the client side, which means a bot can just inject a fake token and sail right through. You have to verify every token against a provider API on the server. There's no exception on that. The third layer is a WAF integration. Cloudflare or Google Cloud Armor sitting in front of the application intercepts suspicious traffic at the network edge before it even reaches your login endpoint. Rate limiting and IP reproduction blocking happens upstream. The fourth layer is a honeypot field. It's hidden from input the real user. It's hidden from input that real users never see and never fill in. A bot that programmably fills every field will fill it. You see a value in there. You simply reject the submission. It's completely free to add, and it catches a lot of bots basically. None of these alone is the answer. The whole point is that you layer them. So you might have 2 and 3, or 3 and 4, or maybe all, but that can maybe slow down your website, or maybe get a lot of false positives. But something that needs to be maintained over time, because the attack site keeps getting better, and such statistic defense will eventually stop working. So now we are going to go over the demo. So this is secure login. We have a username called demo user, password is just a bunch of numbers, and we have the captchas. So we can refresh this every single time and get some new captchas. So now we have our solver. So if you just press enter, we have it guessing. We can see it working in real time of what it's doing. So we have 10 attempts, 7 pass, and we have a 70% successful rate. Only one uh, fail. We have a 0. So if you just zoom in for you, um, again, zeros and O's can get the AI thing to mess up because we have a 0 and then an O. So even on here on the terminal, it even shows that we have this stuff getting passed. Then if we look at the server side, we have a lot of get captcha, post get, post get, post get, post get. So if we want to run it again, we can do this. Again, it's solving in super quick, quicker than I can even look and type. Again, another 10 went through, 15 passed, and it has still have a 75% successful rate. All these layers into your website so you can stop what I'm doing. The website doesn't have any of this protections. It's just a HTTP website, so it can just read it. So thank you for watching my demo. I'll get back to the other group.
Hello, my name is Alex Nordberg, and for my part of the project, I will focus on the defensive measures to counteract bots for CAPTCHAs and how to improve the human pass rate for CAPTCHAs. So the problem that we see is we have to get a balancing act between security, the human pass rate, and privacy. With security, we can no longer just keep on making the challenges harder, as AI can just keep on solving the difficulty even while the difficulty increases. What we do see is that the human pass rate goes down as we increase the difficulties, so humans can no longer get through these challenges and are getting blocked. And then with privacy and behavioral score and collecting user data, we're seeing the rising concern of data governance with that third-party data collection risk. And we can no longer assume that AI can match human perception, as we can see that AI can now pass these challenges. So what we can move to is a proof of work challenge, where instead of testing the user, we're testing the browser with a memory bound hash puzzle. This would be almost imperceivable to the user, but when we're testing a bot, the bot would hopefully send millions of requests, and we would try to make it be very computationally heavy, so we could potentially reach token exhaustion. There'd be no behavioral data collected and no privacy concerns with this. Additionally, we can move to adaptive challenges. What this would seek to do is try to move away from the static challenge that we currently have and move to a more interactive challenge, where the AI that's trained now, AI and neural networks that are trained on the old data set, can no longer work, as we'd have shifting space and shifting images. We see that this has been tested before with an under 3% pass rate from AI and neural networks that were tested in this. Additionally, we can move to risk adaptive difficulty, where we would give scores based off of metrics, and if the score is within a passable range, such as we see it as the sessions have low risk, we see a good footprint, the IP has good reputation, and we see normal browsing use, we don't need to really serve a challenge at all. We would only need to serve a challenge if we would see the session as being suspicious. And then if so, we keep on seeing that behavior, we could escalate the difficulty of these puzzles. And this would try to give the users, legitimate users, no challenges and less friction, while we could attempt to give the bots more difficulty and more work to hopefully stop them without impacting the legitimate traffic that's coming through. Lastly, we can work on a layered defense and focus on server-side validation. For this layered defense, we can do the web application firewall rules combined with behavioral scoring. We could set up honeypots, and then lastly have the caption as the last layer. And with the CAPTCHA, we should always focus on server-side. As with client-side, a lot of the times these checks can be bypassed by anybody who just understands protocol. This most likely likely being AI that could understand the protocol. What we're trying to do is show no challenges to low risk sessions. Legitimate users shouldn't see captures at all. The challenge should only appear if we believe they're suspicious. The proof of work, this would be moving from the user's perception, and we want to give them near zero cognitive load, and we would like to achieve zero accessibility barriers. These need to be tuned constantly. We can't just set what we believe the session to be once. We have to go back and actively monitor these sessions. The multiple layers of defense, where we see honeypots being used, the web application firewalls, along with IP checks to try to catch bots. And these would all be ran before any user-based challenge is put out. And what we see is that static images and capture images are very easy to bypass. Behavior scoring alone, although we can try to detect humans, bots can also try to mimic this. Where we start seeing like real benefit is with proof of work, where we're no longer putting any of the work on the user, but we're putting it on the browser and trying to make it very costly for the bots. The most beneficial one that we see is the adaptive inlayer approach.